Hi, my name is Ahmad Ademiri, and I'm going to talk about exchange of greenhouse gases between soil and atmosphere. Introduction: Soil and its use contribute substantially to the greenhouse effect, the enhanced warming of the Earth's surface and lower atmosphere as a result of increased emission of carbon dioxide and trace gases into the atmosphere by human activity over and over any warming due to natural processes. The most important individual greenhouse gas is carbon dioxide CO2, but substantial contributions to global warming are also made by methane, CH4, and nitrous oxide and N2O. A further contribution to global warming comes indirectly from tropospheric ozone, which is produced by light catalyzed reactions involving nitric oxide, NO, and organic compounds like isoprene monoterpenes emitted by vegetation. Nitric oxide is a natural product emitted from soil as well as from combustion. Soil, particularly in its undisturbed natural state, also acts as a sink for methane already in the atmosphere. These gases are all produced or consumed as a result of microbial processes in the soil, but the size of the fluxes between the soil and atmosphere depends heavily on soil physical factors. Soil temperature and water content directly affect production and consumption of greenhouse gases through their effect on microorganisms and root activity. This review examines the interactions between the controlling physical factors and the biological processes responsible for trace gas production and consumption in soil. Now we have physical controls and on CO2 emission from soil. Temperature. One of the studies has suggested that the temperature sensitivity of soil respiration may be independent of the mean annual temperature of the soil across a wide variety of ecosystem and average temperature characterizing the temperature response for forest soil is particularly important because this soil contains more than 70% of the world pool of carbon in the soil. The release of CO2 from soil organic matter by heterotrophic respiration, and where roots are present, The release by autotrophic root respiration generally increase exponentially with temperature. The, research, the researchers commented that ideally temperature dependence of CO2 production would be determined both in field measurement and in models for each soil horizon rather than relating total soil CO2 efflux to the temperature of some arbitrarily chosen depth. XU and QI 2001 have related Q10 measurements to temperature readings at various depths in the pine plantation in the Sierra Nevada of California and found an increase in Q10 with increasing depth in the soil. Soil water content and aeration. Soil water content, in particular water filled pore space WFPS, is another variable that affects the rate of respiration. Example XU and QI 2001b. There is a wide range of water contents within which there is little change in the rate, but as the soil dries, there comes a point at which microbial activity is inhibited and respiration decreases. Ray et al. 2002 investigated the relation between soil respiration, volumetric water content, and the temperature of the soil for a Mediterranean site. He found that whenever the water content was more than 20%, soil respiration was controlled by temperature, and during the dry summer, respiration was limited by the lack of water. In very wet soils, aeration is restricted because a large proportion of the pores are filled with water. Respiration is also restricted and CO2 flux decreases, but not as much as when lack of water is the limiting factor. Physical control on CH4 emission and soil oxidation. Now, CH4 emission. The concentration of methane in the atmosphere has more than doubled since the pre-industrial era, from about 0.7 multiplied by 10 to the power 6 minus 6 mole to more than 1.6 multiplied by 10 of the power minus 6 mole, which is today. Most atmospheric methane is destroyed by oxidation by UV created hydroxyl radicals OH, while 5 to 10% is removed from the atmosphere by diffusion into aerobic topsoils, where it is oxidized by soil microorganisms. No side, no single source is responsible for the atmospheric increase, but soils contribute about 40% of total emissions, rather total emissions. Physical controls on N2O and NO emissions. Diffusion of CO2 and N2O, nitrous oxide N2O and nitric oxide NO are produced in soil, mainly in the course of two contrasting microbial processes. Nitrification of ammonium NH4 to nitrate NO2 and thence to nitrate NO3 and denitrification of nitrate to N2O and ultimately to molecular nitrogen N2. The rate of nitrification, the rate of N2O production, and the ratio of N2O to nitrate produced during nitrification all increase as the soil WFPS increases. Production of NO by nitrification is generally much faster than the corresponding production of N2O, and this is reflected in the ratios in which the two gases are emitted from irritated soils. Now, conclusion. This review provides a bridge between soil physics and soil biology by demonstrating the key roles played by soil physical factors in controlling the biological processes responsible for the exchange of greenhouse gases between soil and atmosphere. The release of CO2 by aerobic respiration is a non-linear function of temperature over a wide range of soil water content, but becomes a function of water content as a soil dries out. The main control on oxidation rate is gas gas diffusivity, and the temperature response is small. Nitrous oxide is the third greenhouse gas produced in soils, together with NO, a precursor of tropospheric zone short-lived greenhouse gas. Emission of N2O increases markedly with increasing temperatures, and this is attributed to increases in the anaerobic volume fraction brought about by an increased respiratory sink for O2. Increases in water-filled pore space also result in increased anaerobic volume. Again, the outcome is an exponential increase in N2O emission. Future study the impact of this effect on differences in respiration rate between organic and mineral soils also needs to be investigated before any satisfactory upscaling of respiration measurement at particular study sites to a regional or national basis can be achieved. And this is my reference. Thank you so much.